Okay, electric field points in the direction of decreasing potential. Positive charges want to go towards lower potential on their own. All right, today, so I just wrote that here. Again, the units for electric potential are volts. We use capital V for volts. And what I think we're going to do, now let me just talk for a minute about equipotential surfaces, and then we'll do a little worksheet and see if we've see if you've got the difference between potential and electric field and things like that. So we did this in lab, but if you have charges, let's just make how about a plus and a minus? 2-point charges. The electric field lines, what should I use? Blue? Go from the positive to the negative. And how about our equipotential surfaces? And if our negative charge, we could call that 0 volts. And if our positive charge was something like 20 volts, then this one would probably be 10 volts. It would be 10 volts. And then if we moved a little bit closer to the negative charge, to the lower potential, we'd find a spot that was a little less. Let me see, how many do I want to draw here? Over here maybe. This would be probably 8. And we could keep going. These would close. If we had a big enough piece of paper, this first one I drew, those lines just keep going. It's a straight line, right? It goes to infinity. But this is a curved path. Where's this going to end up going? It's going to loop all the way around, and it's going to close over here and loop back to itself. It's going to form a big teardrop or whatever shape that is, right? It's going to get crunched in a little bit on this side, but it's going to spread out on the other side. We'll see it as we draw some smaller ones. You'll see the shape. Okay, so then there'd be another one in here, maybe 6 volts. Something like that. And you could keep going. I'll draw one more, maybe. Okay, and it's symmetric, so we get this particular charge distribution is symmetric, right? A point charge here, a point charge here. So this is going to be symmetric. The lines on the other side would be symmetric, and those would go up to 12, 14, 16, 18, right? We could draw them on the other side. So you get the idea. So what are the special properties of these equipotential lines? The first thing we know is that it's like a topographical map. You walk around the line on a topographical map. What does it mean? It means you don't never change elevation, right? Each line on a topo map is a constant elevation. So if it's like you're walking around the top of a hill, but you'd be at the same elevation the whole time. So in this case, if you were walking around this path, you would always be at 16 volts. You'd be at the same electric potential everywhere on that line. And we know that it takes work to move a charge with or against an electric field. So if we are staying, and we can look at the change in electric potential and figure out the work done, right? So if we're staying at the same potential, does it take any work to move a charge around there? No work. So if we moved a charge along one of these red paths, it takes no work, because the electric field at every instant is perpendicular. Maybe I didn't draw it so well. These are a little bit better. The electric field is always perpendicular to the electric potential, the equipotential line. So let me try to draw some. These are perpendicular to each other. Perpendicular. Okay? And because they are always perpendicular, you get the idea. Because they're always perpendicular, as you're moving along the red path, the electric field is always perpendicular to it. It's never pushing with you or against you. So it's like moving it's like lifting up a big suitcase. You do work lifting it up, right? You walk across the room, you do no work on the suitcase against gravity. I should say gravity does no work, right? So you lift it up, gravity does work on it. You walk across the room, gravity does no work on it, right? The force of gravity is perpendicular to its path the whole time. So the same is true here. You can move along these equipotential surfaces and no work is done, no force is required, because it's the force is always perpendicular to those positions. So the one thing we know is that these lines are constant potential. The other thing we know is the electric field lines are always perpendicular to those. And any metal surface, any conductive surface, is an equipotential surface. The potential is constant everywhere on a conductive surface. So what does that mean? It means that, well, we'll get there in a second. What it means is that about nice symmetric shapes like spheres. And what happens when you put some excess charge on a sphere, on a conductive sphere? Goes to the outermost surface, right? Because those charges are free to move on a conductor, and they want to get as far apart from each other as they can. So where do they go? To the outermost surface, and they distribute uniformly. If we have something that looks more like a odd shape, and we put excess charge on it, like a peanut or something. This is, I don't know what this is. Lima bean or something. Put some excess charge on it. The charge will group up where the radius of curvature is smallest. And why does it do that? Because it wants the potential to be the same everywhere. So let's take a look at what happens, how we can figure out the electric potential on a conductive sphere or shape like this.